you have a lock with 4 wheels. Each wheel has slots from 0 to 9, and the wheels can rotate freely and wrap around. So you can turn 9 to 0 and vice versa. So if the lock initially starts at 0, 0, 0, 0, and you're given a list of dead ends, which are codes that you have to avoid, because if the lock displays any of those codes, then the wheels of the lock will stop turning. Then given a target representing the value of the wheels that will unlock the lock, return the minimum total number of turns required to open the lock, or -1 if it's impossible.
Yeah, perfect. Okay, so if I may, I would like to start by going through the given example to see if I understand the problem correctly. Okay, so we start at position, let me type below. So we start at position 0, 0, 0, and we want to go to the target, which is 0, 2, 0, 2. So we turn, let's say, the second wheel. We see if that's not a dead end, that's not a dead end, perfect. So we would like to turn the other wheel. If I turn this one, I will reach a dead end. If I turn the last one, I also reach a dead end. So if I start from the last one before, I will also have the same issue. So I have to increment any other wheel in this example. So let's say it will be the first one. Let's see what happens. Okay, and now I can turn the second one as I wanted. And now I can start turning the last one. I'm not reaching, there's a dead end with 1 at the beginning, but I'm not hitting that. So I have 1, 2, 0, 1, and then I have 1, 2, 0, 2. And now I have to go back with the first wheel. So it will be 0, 0, 2. Okay, it makes sense because the output is 6, and I think I had 1, 2, 3, 4, 5, 6 steps. So that's perfect. Okay, so it really shows that I don't have to follow the intuitive path, which is incrementing the numbers by one. I have to really look for those dead ends. Okay, so I would like to start with some naive approach, which will be turning all the wheels in each direction, hoping to reach the solution. And basically, when I reach a dead end, I will backtrack. I see a couple of problems with this solution because basically, if I even reach the target, I'm not sure if that's the shortest path. I would have to try all of the possible combinations to be sure that the found path is the shortest. But let's see how it goes if I decide to follow this approach, right? So I would start with 0, 0, 0. And I can see already that I have multiple options at next step. I can do 1, 0, 0. I can do 0, 1. I can do 0, 0, 1, 0. But I also can go backwards, like to 9. So I can have 9, 0, 0, 0, 9, 0, 0, 0, 0, 0, 0, 9. Okay, so I think that those are all combinations. So it looks like I have 8 possible options at each step. And then if I choose one of them, then again, I have 8 options. Probably 7 because I shouldn't go back to the visited node because that won't be the shortest path. But yeah, so what I can see from here is that that's a graph because basically I have those multiple nodes. From those, I have following nodes and so on. It's not a tree because like the same node can appear I can reach the same node multiple ways. So it's a graph structure. Yes.
Can you tell me what the nodes and the edges of this graph represent?
Yes. So the edges of the graph are the combination, the 4-digit combination on the log. And edge is a term, right? A change of 1 digit, 1 up or 1 down.
Yeah. Okay. So you're saying then that there's an edge between 2 nodes if there are 2 combinations that are only 1 turn apart.
Yes.
Okay. Great.
Okay. Great. So as I said, I know that's a graph, and I have to reach one node, which is 0, 0, 0. I mean, from 0, 0, 0, I have to reach the target node, which is given in the input. So basically, that's a graph traversal. And there are two popular algorithms, like graph traversal algorithms, which I can consider here. So one of them being depth first search, the other one being breadth first search.
Yeah.
Yes, so let's have a look at depth first search. So if I go this path, I go deep into one edge. So I'm reaching the same problem I had in the brute force solution. Like that's basically a brute force solution, which I explained earlier. So even if I reach a target node, I don't know if that's the shortest path.
Right, yeah.
But what I know, if I use the breadth first search, that's actually an extra information which breadth first search gives me. That if I reach a node, I know that's the shortest path because I'm going turn by turn, layer by layer. So I'm starting from the closest nodes. I'm going from the nodes one turn further, and so on and so forth. So when I reach a target node for the first time, I can be sure that's the shortest path, and that's what breadth first search allows me to do. Does it sound good to you? Is it should I try to implement the breadth first search algorithm? Or
Makes sense to me.
Okay, perfect. So I will start. Okay, so I would like to have a function. I'll make it static so I can call it and I later test it from the main method. I'm returning number of terms, which is an integer. The name of the method, let's call it openlock. Okay, perfect. So to make it simpler, I would prefer, if that's possible, to have a set. Sorry, I have a string, okay, integer. And I have that ends. Okay, perfect. So I have also target. Okay, so what I would like to do first, also doing my work, is to check for edge cases in this function. So I'm assuming those values are not null, like this is handled outside, but still I can see scenarios which will complicate things for me. So one of them being like, if the dead end is at the beginning, 0, 0, 0, like there's no solution because lock is just broken. I cannot move.
Yes.
So let's check for that. Okay, the other scenario would be the opposite. So the dead end contains the target, which basically means that I cannot reach the target value because it will break the lock. So for those both, I have to return -1 was in the explanation of the problem. But, okay, my formatting maybe not the best. But should no, I can't. Can I? No. Okay. Let's keep it this way. Maybe one line below. Okay. So I will return -1. Or maybe I will move this to the right. Okay, that's better. Perfect. Okay, so let's continue. So I would like to implement the breadth first search. One thing I have to keep in mind, I don't want to revisit the nodes, right? First time I revisit the nodes, that's the shortest path. So I don't need to revisit. So I have the set of visited nodes, which I will check at each step.
Okay.
Okay. So I can immediately add the first node. Okay, let's do that. Because I will process the first node below. So what I want to do is, for purpose search, we always need the queue. And now I add, as I mentioned, the first element to the queue. We need at least one element so we can process it. Start from there because, yeah, so also maybe I will put my result now, which will be number of terms. So if the answer, if the target is 0, 0, 0, that's 0. So this is like fully processed. So yeah, if that's the answer, if that's target, that's the answer. This shouldn't be so easy all the time. So I need a while loop, which will go layer by layer, which will do the terms basically. So we have a queue, we have the while loop, check it until the queue is empty. Now we do the trick where I get the size of the queue. So because I want to increment the terms, so I need to count the layers. So now I know that in the queue I have the 0 layer, which is my 0 element. Then I will add those 8 elements, which are neighbors. So then in the next iteration, the size will be 8. So I will iterate in the for loop over those 8 nodes, and only after that I will increment the terms, because I want to count children. I want to count the distance from the start node.
Right.
That's why I need this for loop inside.
Yeah, because all of the 8 in that queue are the same distance away from the source right now.
Yes, exactly.
Okay.
Okay. Perfect. So what can I do now? Well, maybe I will take an element from the queue. As I mentioned, I will also, so I won't forget about the terms. So when I take element from the queue, that's current. It can be an answer. I need to be ready for that. So if current equals target, I return terms. Also, I can return something after while loop -1, so I didn't find the result. Okay, so for the 0, 0, that will be 0, 0. Works fine so far. Now I want to iterate over each wheel and make a turn in each direction. So we have, it's a fixed number, I know it's 4. So iterate from 0 to 3. Okay. So here I'm getting the next digit. Okay. So next digit at the position 0. So I need to take from my current. Okay. So from my current element, I take the digit at the position 0, and I want to go. I need to convert character into integer. That's how we do it in Java. And then I want to go by 1 up. Okay, so what I have to look for are some edge cases. One edge case, which is 9. So if I have 9, I go up. I don't go to 0. I don't go to 10. I go to 0. So how I can solve that? Because here I have 10. I can just take the modulo 10.
Okay, perfect.
Yes. So okay, so that's really good. Now I construct a new string. Next is available. Okay, next. So I have current. I have the string 0 to j. I add my next digit. Just constructed, and then I add remain. I forgot I cannot copy it. So let's type again current +1. Okay, this one should work. Okay, so I have the next element, which I will need to add basically back to the queue. But before that, I need to check for my dead ends and for my visited array. So because if it's a dead end, then I shouldn't add. Only I add when it's not.
Okay.
Or can also be visited. Okay, but if it's not, then I can add it my queue and process it. So like this, also mark it as visited on this stage because I had to check for it. Perfect. So that's turning up. Let's try turn down. So do it below. So okay, I really want to. Okay, I can copy. Perfect. So I go down, so I do -1. So my edge case now is 0. If I do 0 -1, then I have -1. So what I can do is +10. If I add +10, then I have 0 -1 +10 is 9. It's perfect, but also for 9 I have 19. Sorry, if I have 9, I go -1, I have 8 +10 is 18, modulo is 8. So it works for both edge digits. This formula. So this one also will be copied probably over. So I can already see that there is some repetition. I can probably replace it by 9, but what I would like to do, maybe to clean it up a little bit, because like the only difference here is -1 and 1, because I can add them here, and that doesn't matter anything because there's a modulo. So like the only difference between those two parts, oh sorry, this should be also copied. Yes, I need to construct the next string actually. Yeah, so the only difference would be basically this -1. So that's why I would like to do a wrapper around it. So basically I will iterate from -1 to 1. So I have a for loop with 2 elements. When I have -1 and 1, so I can repeat this part of the code.
Okay, great.
So, okay, -1 plus 2 is 1, which is smaller than this. That's what it should like. Okay, so okay, works. And this is my M. Okay, perfect. So here I do my, okay, so maybe like this. So first I do -1, then I do +1. Have my formula, I have my next. Constructed correctly, check contains, add. Okay, I return terms, I check terms. It should work. I hope I didn't miss anything. Yeah, so should I test it?
Yeah, I'd love to see you test it out on a few test cases.
Okay, let's see if it works. So do it in the main method. So basically, I have a set, okay. Like that, and okay, so I have to, now I have one test case here, so I'll use this one which I have. Copy 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. Okay. Now I can call my function print result. Okay. my target will be okay, so I have my set, I'm calling my function, I'm printing the result. Let's go see what happens. Doesn't work. String cannot be converted to ints. My target should be a string. Okay. 4, and it should be 6. Interesting.
It found
Almost there. So I found a shorter path. Maybe that's good. Okay, let's see. So we're not in the edge case. I added the visited. I have the queue. I have my size. I'm iterating over. I have the element which I get from the queue. If it's equal target, I return terms. 0. 0 should be fine. Then I iterate over 0, 1, 2, 3 indexes. I get -1, 2. Yes, it should be -1 and 1. So next digit, I get a digit. Yes, that's a char. Okay, so I have 2, 1.
Is there a way to find out what the path actually is that it computed?
Okay.
Clear what the bug is.
I'm thinking with this. I mean, I can print all the nodes I pull. Looking for visit, I check for that, and looks legit. Okay. Yeah, increment the terms. Okay. So let's print all of the. Yeah, that's what I thought. I should also print parents. Okay. On the phone. I print any terms. Okay, so that's very, very long. Why can I clear? Okay, yeah, that's something. Okay, so why it's not printing terms? Oh, it's printing here. Okay, so turn 1. So I go to as expected. I have 8 options. Then it will be much more. So 8 for each 8. Yes, it's 23. 33 is already huge. And what is 34? Because before I return, I read the target, but okay, I can see no. Yes, I went from like 0 to 0, 1. 0 to 0, 1. That's not, and that's it looks like, because yeah, so I shouldn't add that. So for some reason, even though it's a dead end, I added it.
Yeah, this statement is an or right now, right? Should it be an or necessarily? Because then that does allow you to visit.
Yes, you are right. Yes, yes. Okay, perfect. Yes, because it cannot be a dead end and it cannot be visited because yeah, okay.
Yeah.
I started without the negation and I forgot to flip that. Okay, cool. So maybe to make it cleaner, I'll remove it temporarily, the printing.
Yeah, let's see if it works now.
Okay, 6 works now.
Nice job.
Perfect.
Okay,
yes.
Great. So you don't necessarily have to implement this, but like if you were to test other test cases, what are some other test cases that you would try?
Okay, so I think that this one, which I already tried, is quite complex. because yeah, I fall into this trap that I have to avoid the dead end, and I didn't. So I think it's quite complex. I can try edge cases, so I can try like going from 0, 0, 0 to 0, 0, 0, or having a 0, 0 as a dead end, or having something where there is no path. So yeah, so dead ends doesn't allow me to go there.
Yeah, what would make it impossible to reach a particular point?
Yeah, so for example, I here have all children from 0, 0, 0. So if those are dead ends, then I cannot reach basically anything which is other than those combinations.
Yeah. Okay.
That's
All
an
right.
example.
Cool. So what about the runtime of this algorithm then?
Okay, so what's about the time complexity? Okay, so how time complexity works is that usually it's proportional to the input. And in our input, we have dead ends. And we are not doing pref search on dead ends. We are doing pref search on the log. And log is like more fixed because there's only 4 wheels. So what I can see, maybe I put a bit below. Yeah, so if I look at my dead ends, am I doing anything with them? Not really. I have the set. I'm not iterating over them. So say can be constant. But then if I look at the prefer search, so how I can calculate the complexity for prefer search is that basically in the worst case, I'm reaching each possible combination of the log once. And I have the fixed number of combinations because I start at 0, 0, 0, and I'm reaching 999, which sum up to basically 10,000 combinations. So it means that the time complexity of prefer search will be 10,000, which simplifies to constant time complexity in this example.
Okay, and that's with respect to just the number of elements in the dead ends list, right?
Yes, because that's the only input which is changing. So that's my n, but I'm not doing anything with the dead ends instead of checking contains, which is constant time. So that's why this constant time. My prefer search, yeah, it's fixed. It's only always 4 wheels, so it doesn't depend how big the dead ends are. The worst case is the same here.
Okay, cool. Okay, so to make this slightly more challenging then, what if in this problem instead you also got as a variable like the number of dials in the lock? So then what would the runtime be?
Yes, that's more complicated. So the calculated dead ends would be also like 0, 1. What I'm thinking is that in the worst case, I don't have any dead ends because then my prefer search will go through more elements because basically I remove dead ends from the nodes I visit. So if I calculate the worst case complexity, I shouldn't consider dead ends, but I should consider numbers of wheels because that changes nodes in my graph, and that impacts the complexity. So how I can calculate that is that there is this formula which returns the time complexity for prefer search. So that's vertices plus edges, that's the worst case time complexity. So in my example, that will be basically the number of vertices is yeah, so for each digit I have 10 combinations. I mean, for each wheel I have 10 digits, so 10 possible combinations. And then I have n wheels, so that's 10 to the power of n, a number of combinations on the log. And then I add number of edges. So how I can do that? So this will be basically, so what I'm thinking is that I have a node. So from this node, I have, in this example, I have 8 combinations. So how it works is that when n is number of wheels. It's 8, so it's 2. Because here I can do 2 moves, so that's 2 plus 2 plus 2 plus 2. So it will be like 2 multiplied by n.
Okay.
So where n is 4, that's 8. Makes sense.
You're saying every node has 2 n neighbors where n is a number of dials.
Yes. So I know the number of vertices, so it's 10 to the power of n. I know the number of edges for each node, which is 2 multiplied by n. Okay, but I cannot calculate edges twice because for 2 nodes I have 1 edge, because I have to divide by 2.
Yep.
So maybe let's do this. Okay, so if I simplify it, I remove the 2's, and that should be something like n plus 1 multiplied by 10 to the power of n, something like that.
Okay.
Cool.
Okay, cool. Yeah, so our runtime ends up being a little bit more complex that way then.
Yes, a lot more complex, I would say. At least to calculate it, yes.
Yeah, all right, fantastic. You did a great job. I'd love to pause here and get your take on how this interview went. Like, what do you think went really well for you, and what do you think you would change going forward?
Okay, so maybe I would like to start from what I would change. I think maybe a mistake was I was going too fast. I don't know if that's stress or what, but I was typing code really fast, and I didn't maybe think it through. So that's why I did like a silly mistake with the or. Like I had to. I didn't have the negation, that I switched it without thinking it through. So I forgot to switch this one. So maybe I should see why I'm doing that. So I think maybe the speed was the factor I did this silly mistake. So that's one thing. What went wrong, what went good. I think usually in those problems, we can specify our own input. So I think I did a good job using a set.
Yeah.
Because I could use it directly. I didn't have to rewrite elements. If I had to rewrite elements, then I could have like O(n) time complexity. Yeah. And filtering this time complexity was not straightforward. So that could be something which will make my solution worse at the end. So I think that was a good choice. Yeah, for sure. That definitely made it a lot more efficient. Okay, yeah, I had some very similar thoughts as well, but I also really like that in the beginning you started by working through some examples first, because that always helps you clarify your logic. And then you managed to recognize right away that you can solve this problem using a graph representation. And like as soon as you notice that, then it becomes much more straightforward to identify like, oh, it's a type of traversal that we need in order to solve this. You also did a great job of identifying the differences between a DFS and a BFS and showing us that like you can only really solve this with a BFS. In addition, with your implementation, I like that you use a queue instead of the recursive implementation of BFS, because that does get rid of the space that you would need to store the function stack. So that was awesome as well. Yeah, and lastly, I like that when you were writing the code, you also focused on removing duplicate code as you went. So then the code ended up being a lot more concise than it was before. Yeah, so as for things that like might help in the future, I think one thing with writing code that is a little bit more complicated in logic is that sometimes it helps to make things a little bit more modular. So one example could be like, so this loop that does for like m equals -1 from on line 48, we could instead first have a function that says like, oh, get neighbors of the current node, and then just loop through the neighbors. And then it's maybe like that requires like an extra function, but it does make it a little bit cleaner to read, and then you lessen the chance of having bugs, I would say. Yeah, otherwise, I thought you did a really great job. Thanks for joining us today and showing us how to solve this problem. Yeah, thank you for the very good feedback. Yeah, had a great time.
All right, thanks for watching, everyone. Bye.
Thanks so much for watching. Don't forget to hit the like and subscribe buttons below to let us know that this video is valuable for you. And of course, check out hundreds more videos just like this at tryexponent.com. Thanks for watching and good luck on your upcoming interview.